Bohr's model of hydrogen atom, proposed by Niels Bohr in 1913, was the first quantum model that correctly explained the hydrogen emission spectrum. Bohr's model combines the classical mechanics of planetary motion with the quantum concept of photons. Once Rutherford has established the existence of the atomic nucleus, Bohr's intuition that the negative electron in the hydrogen atom must revolve around the positive nucleus become a logical consequence of the inverse square distance law of electrostatic attraction. Recall that Coulomb's law, describing the attraction between two opposite charges, has a similar form to Newton's universal law of gravitation, in the sense that the gravitational force and the electrostatic force are both decreasing, as 1 over r squared, where r is the separation distance between the bodies. In the same way as the Earth revolves around the Sun, the negative electron in the hydrogen atom can revolve around the positive nucleus. However, an accelerating charge radiates its energy. Classically, if the electron moves around the nucleus in a planetary fashion, it would be undergoing centripetal acceleration, and thus would be radiating energy that would cause it to spiral down into the nucleus. Such a planetary hydrogen atom would not be stable, which is contrary to what we know about ordinary hydrogen atoms that do not disintegrate. Moreover, the classical motion of the electron is not able to explain the discrete emission spectrum of hydrogen. To circumvent these two difficulties, Bohr proposed the following three postulates of Bohr's model. First, the negative electron moves around the positive nucleus, the proton, in a circular orbit. All electron orbits are centered at the nucleus. Not all classically possible orbits are available to an electron bound to the nucleus. Then, 2. The allowed electron orbits satisfy the first quantization condition. In the nth orbit, the angular momentum, L sub n, of the electron can take only discrete values, like L sub n is equal to n, h, where n is equal to 1, 2, 3, and so on. Then, lastly, an electron is allowed to make transition from one orbit where its energy is E sub n to another orbit where its energy is E sub m. When an atom absorbs a photon, the electron make a transition to a higher energy orbit. Where an atom emits a photon, the electron transits to a lower energy orbit. Electron transition with the simultaneous photon absorption or photon emission takes place instantaneously. The allowed electron transition satisfies the second quantization condition, where HF is equal to E sub n minus E sub m, where HF is the energy of either an emitted or an absorbed photon with the frequency F. The second quantization condition states that an electron's charge in energy in the hydrogen atom is quantized. These three postulates of the early quantum theory of hydrogen atom allow us to derive not only the Rydberg formula but also the value of the Rydberg constant and other important properties of the hydrogen atom, such as its energy levels, its ionization energy, and the sizes of electrons' orbit. Note that in Bohr's model, along with two non-classical quantization postulates, we also have the classical description of the electron as a particle that is subjected to the Coulomb's force, and its motion must obey Newton's law of motion. The hydrogen atom as an isolated system must obey the law of conservation of energy and momentum in a way we know from classical physics. Having this theoretical framework in mind, we are ready to proceed with our analysis. Electron orbits. To obtain the size r sub n of the electron's nth orbit of the electron speed v sub n in it, we turn to Newtonian mechanics. As a charged particle, the electron experiences an electrostatic pull toward the positively charged nucleus in the center of its circular orbit. This electrostatic pull is the centripetal force that causes the electron to move in a circle around the nucleus. Therefore, The magnitude of centripetal force is identified with the magnitude of the electrostatic force, where ME V squared sub n over R sub n is equal to 1 over 4 pi E 0 times E squared over R squared n, where E denotes the value of the elementary charge. The negative electron and positive proton have the same value of charge. The Q equals to E. When it is combined with the first quantization condition, we can solve for the speed V sub n and for the radius R sub n, where V sub n is equal to 1 over 4 pi E0 and E squared over H times 1 n. And for the radius R sub n is equal to 4 pi E0 times H squared over ME E squared times n squared. Note that this result tells us that the electron speed as well as the radius of its orbit depend only on the index n that enumerates the orbit, because all other quantities in the preceding equation are fundamental constant. We can see that the size of the orbit grows as the square of n. This means that the second orbit is 4 times as large as the first orbit, and the third orbit is 9 times as large as the first orbit, and so on. Also, we can see that the electron speed in the orbit decreases as the orbit size increases. The electron speed is the largest in the first Bohr orbit for n equals 1, which is the orbit closest to the nucleus. The radius of the first Bohr orbit is called the Bohr's radius of hydrogen, denoted as A sub O. Its value is obtained by setting n is equal to 1, where A sub O is equal to 4 pi E0 times H squared over ME E squared equals to 5.29 times 10 raised to 11, and M is equal to 0.529. We can substitute A sub O to express the radius of the nth orbit in terms of A sub O, where R sub n is equal to A sub O n squared. This result means the electron orbits in hydrogen atom are quantized because the orbital radius takes only specific values of A sub 0, 4A sub 0, 9A sub 0, 16A sub 0, and so on, and no other values are allowed. Okay, let's proceed to electron energies. The total energy E sub n of an electron in the nth orbit is the sum of its kinetic energy, where K sub n, and its electrostatic potential energy, U sub n. We find that K sub n is equal to 1/2 ME V squared sub n is equal to 1 over 32 pi squared E squared 0 times ME E 4 over H squared and 1 n squared. Recall that the electrostatic potential energy of interaction between two charges, Q1 and Q2, that are separated by a distance R sub 12 is 1 over 4 pi E0 times Q1 Q2 over R12. Hence, Q1 is equal to positive E is the charge of nucleus in the hydrogen atom, the charge of the proton. Q2 is positive E is the charge of electron, and R12 is equal to Rn is the radius of the nth orbit. Now we can use to find the potential energy of the electron, where Un is equal to negative 1 over 4 pi E0 times E squared over Rn is equal to negative 1 over 16 R squared E squared times ME E raised to 4 over H squared and 1 over n squared. Note that the energy depends only on the index n because the remaining symbols are physical constant. The value of the constant factor is E0 is equal to 1 over 32 pi squared E squared sub 0 times ME e raised to 4 over h squared is equal to 1 over 8 e squared sub 0 times ME raised to 4 over h squared is equal to 2.17 times 10 raised to negative 18 joules or 13.6 eV. It is convenient to express the electron's energy in the nth orbit in terms of this energy as E sub n is equal to E0 times 1 over n squared. The index n that enumerates energy levels in Bohr's model is called the energy quantum number. We identify the energy of the electron inside the hydrogen atom with the energy of the hydrogen atom. Note that the smallest value of energy is obtained for n is equal to 1. So the hydrogen atom cannot have an energy smaller than that. The smallest value of the electron energy in the hydrogen atom is called the ground state of the hydrogen atom, and its value is E sub 1 is equal to E sub 0 is equal to negative 13 eV. The hydrogen atom may have other energies that are higher than the ground state. These higher energy states are known as excited energy state of hydrogen atom. There is only one ground state, but there are infinitely many excited states because there are infinitely many values of n. We say that the electron is in the first excited state when its energy is E sub 2, where n is equal to 2. The second excited state when its energy is equal to E sub 3, when n is equal to 3. And in general, in the nth excited state, when its energy is En plus 1, there is no highest of all excited state. However, there is a limit of the sequence of excited state. If we keep increasing n, we find that the limit is E sub 0 over n squared, where 0. In this limit, the electron is no longer bound to the nucleus, but becomes a free electron. An electron remains bound in the hydrogen atom as long as its energy is negative. An electron that orbits the nucleus in the first Bohr orbit, closest to the nucleus, in this ground state, where its energy has the smallest value. In the ground state, the electron is most strongly bound to the nucleus, and its energy is given by. If we want to remove the electron from the atom, we must supply it with enough energy, E sub infinite, to at least balance out its ground state energy E sub 1, where E infinite plus E1 is equal to 0. E infinite is equal to E1 equals E sub 0 equals E0 is 13.6 eV. The energy that is needed to remove the electron from the atom is called the ionization energy. The ionization energy, E sub infinite, that is needed to remove the electron from the first Bohr orbit is called the ionization limit of the hydrogen atom. The ionization limit in that we obtain in Bohr's model agrees with the experimental value. The energy spectrum of the hydrogen atom, energy levels, horizontal lines, represent the bound state of an electron in the atom. There is only one ground state, n is equal to 1, and infinite quantized excited state, the state that are enumerated by the quantum number, n is equal to 1, 2, 3, 4, 5, and so on. Vertical lines illustrated the allowed electron transition between the state. Downward arrows illustrate the transition with an emission of photon with a wavelength in indicated spectral band. Okay, let's move on to the spectral emission lines of hydrogen. To obtain the wavelengths of the emitted radiation, when an electron makes a transition from the nth orbit to the mth orbit, we use the second of Bohr's quantization condition. And for energies, The emission of energy from the atom can occur only when an electron makes a transition from an excited state to a lower energy state. In the course of such as a transition, the emitted photon carries away the difference of energies between the state involved in the transition. The transition cannot go in the other direction because the energy of a photon cannot be negative, which means that for emission, we must have an En is greater than Em and N is greater than M. Therefore, the third of Bohr's postulate gives Hf is equal to En minus Em is equal to En minus Em, and E0 times 1 over N squared plus E0 times 1 over M squared, where E0 parenthesis 1 M squared minus 1 over N squared. Now we can express the photon's energy in terms of its wavelength. Hf is equal to Hc over lambda, and divided by both sides by Hc. Then the result is 1 over lambda is equal to E0 over Hc times 1 over M squared minus 1 over N squared. The value of the constant in this equation is E0 over Hc is equal to 13.6 eV over 4.136 times 10 raised to negative 15 EVs times 2.997 times 10 raised to 8 meter per second is equal to 1.097 times 10 raised to 7 1 over M. This value is exactly the Rydberg's constant R sub h in the Rydberg heuristic formula. In fact, is identical to the Rydberg formula because for a given M, we have N is equal to M plus 1 and M plus 2 and so on. In this way, the Bohr quantum model of the hydrogen atom allow us to derive the experimental Rydberg constant from the first principle and to express it in terms of fundamental constant. Let's move on to the second topic, the de Broglie's explanation to the quantization of angular momentum of electron. But first, we will define what is angular momentum of electron. Angular momentum of an electron by Bohr is given by mvr or nh over 2 pi, where v is the velocity, n is the orbit in which electron is, m is the mass of the electron, and r is the radius of the nth orbit. Bohr's atomic model laid down various postulates for the arrangement for electrons in different orbits around the nucleus. According to Bohr's atomic model, the angular momentum of electron orbiting around the nucleus is quantized. He further added that electrons move only in those orbits where angular momentum of an electron is an integral multiple of h over 2. This postulate regarding the quantization of angular momentum of an electron was later explained by Louis de Broglie. Louis de Broglie, born on August 15, 1892, and died on March 18, 1987, a French physicist best known for his research on quantum theory and for predicting the wave nature of electrons. According to him, a moving electron in its circular orbit behaves like a particle wave. The behavior of particle waves can be viewed analogously to the waves traveling on a string. Particle waves can lead to standing waves held under resonant condition. When a stationary string is plucked, a number of wavelengths are excited. On the other hand, we know that only those wavelengths survive which form a standing wave in a string, that is, which have nodes n at the end. Thus, in a string, standing waves are formed only when the total distance traveled by a wave is an integral number of wavelengths. Hence, for any electron moving in kth circular orbit or radius r sub k, the total distance is equal to the circumference of the orbit, or 2 pi r sub k. And 2 pi r sub k is equal to k lambda. We have the equation 1, where lambda is the de Broglie's wavelength, and we know that the Broglie's wavelength is given by lambda is equal to h over p, where P is the electron's momentum and h is the Planck's constant. Hence, lambda is equal to h over mv sub k. We have the equation number 2, where mv sub k is the momentum of an electron revolving in the kth orbit, inserting the value of the lambda from the equation 2 in the equation 1. And so we get the 2 pi r sub k is equal to kh over mv sub k. And mv sub k and rk is equal to kh over 2 pi. Hence, the Broglie's hypothesis successfully proves Bohr's second postulate. Stating the quantization of angular momentum of the orbiting electron, we can also conclude that the quantized electron orbits and energy states are due to the wave nature of the electron. The quantized emission spectra indicated to Bohr that perhaps electrons could only exist within the atom at certain atomic radii and energies. Recall that quantized refers to the fact that the energy can only be absorbed and emitted in a range of allowed values rather than with any possible value. This diagram of Bohr's model showed the electron existing in a finite number of allowed orbit or shells around the nucleus.